Welcome to this walkthrough of LeetCode problem number 487, Max Consecutive Ones 2. In this problem, we'll explore how to maximize the number of consecutive ones in a binary array when you're allowed to flip at most 1 0. Let's dive into the details and discover effective approaches to solve it. This problem asks us to work with a binary array, which is an array consisting only of zeros and ones. We are allowed to flip at most 1 0 in the array, which means we can change a single 0 into a 1. The goal is to determine the maximum number of consecutive ones we can achieve by performing this operation. For example, if there's a sequence of ones, followed by a single 0, and then more ones, flipping that 0 could extend the streak of consecutive ones. The input is a binary array called nums with a size of n, where each element is either 0 or 1. Our output will be a single integer, representing the maximum streak of consecutive ones that can be formed by flipping at most 1 0. Let's look at some examples to better understand the problem. In the first example, the input array is 1 0 1 1 0. If we flip the 0 at index 1, the array becomes 1 1 1 1 0, creating a streak of 4 consecutive ones. So, the output is 4. In the second example, the array is 1 1 0 1. Flipping the 0 at index 2 turns the array into 1 1 1 1, giving us a streak of 4 consecutive ones, so the output is also 4. In the third example, the input is 0 0 0 0. Here, no matter which 0 we flip, we can only achieve a streak of 1 consecutive 1, making the output 1. These examples help illustrate how flipping a single 0 affects the streak of ones, and our goal is to maximize that streak. There are some important edge cases to consider. First, if the array contains only ones, then the result is simply the length of the array, as no flipping is necessary. Second, if the array is made entirely of zeros, the best we can do is flip 1 0, resulting in a maximum streak of 1. Third, for an array with just a single element, the result is always 1, regardless of whether that element is 0 or 1. Finally, there might be cases where flipping a 0 doesn't increase the longest streak of ones, such as when the array already has a single continuous streak that cannot be extended further. These edge cases highlight the need to carefully handle different input scenarios while solving the problem. To start, let's consider a brute force approach to solving this problem. The idea here is quite simple. We iterate through all possible indices in the array, flipping each 0 to a 1 1 at a time, and then calculate the length of the longest sequence of consecutive 1s in the modified array. By repeating this process for every 0 in the array, we can determine the maximum length of consecutive 1s that can be achieved with a single flip. However, this simplicity comes at a cost. For each 0 in the array, we need to count the length of consecutive 1s, and since this counting itself takes linear time, the overall time complexity becomes quadratic, or O(n squared). On the other hand, the space complexity is O(1), as we only modify the array temporarily without using any additional data structures. While straightforward, this approach is clearly inefficient for larger arrays. Now, to address the inefficiency of the brute force approach, we can use a sliding window technique. The key insight is that we are allowed to flip at most 1 0 into a 1, so we can maintain a window of consecutive 1s that includes at most one flipped 0. Using 2 pointers, left and right, we define the window boundaries. As we move the right pointer through the array, we expand the window and track how many 0s have been flipped. If the count of flipped 0s exceeds 1, we adjust the left pointer to shrink the window until the condition is satisfied again. At each step, we calculate the size of the current window, which is given by right left plus 1, and update the maximum length observed. The beauty of this approach lies in its efficiency. Each element is processed at most twice. This eliminates the need for redundant computations, making the sliding window a powerful and practical solution for this problem. The sliding window approach stands out for its efficiency. The time complexity is O(n), because both pointers traverse the array at most once, avoiding the quadratic overhead of brute force. Additionally, the space complexity is O(1), as no extra data structures are required. These factors make sliding window an ideal choice for this problem. When comparing the two approaches, sliding window is far more efficient and scalable. For large arrays, the brute force solution quickly becomes impractical, whereas sliding window handles larger inputs seamlessly. Furthermore, while brute force is easier to conceptualize, the sliding window technique is still relatively straightforward to implement and avoids unnecessary computations. This balance of simplicity and optimal performance is why we select the sliding window approach as our chosen strategy. Although the sliding window approach is our recommendation, it's worth briefly mentioning the prefix sum-based alternative. This method involves pre-processing the array to calculate prefix sums, which can then be used to determine the maximum length of 1s after a single flip. However, this approach requires additional memory, with a space complexity of O(n), and is generally less efficient than the sliding window in practice. In summary, the sliding window approach is the most practical solution. It offers the best combination of time efficiency, constant space usage, and scalability for larger input sizes. By leveraging the problem's constraints effectively, it delivers an optimal and reliable strategy for solving this challenge. To solve the problem of finding the maximum length of consecutive ones in a binary array after flipping at most 1 0 to 1, we start with a brute force approach. The first step is to iterate through the array. For each index, we check if the value at that index is 0. If it's a 1, we can simply skip that index since there's no need to flip it. Now, when we encounter a 0, we simulate flipping it to 1. At this point, we may create a modified copy of the array to reflect this change, though this step can be adjusted depending on our implementation. Once the 0 has been flipped, the next task is to find the longest sequence of consecutive ones in the modified array. This can be done by scanning through the array again, keeping track of the current streak of ones, and updating the maximum streak whenever we find a longer one. This process ensures that we evaluate the impact of flipping each 0 in the array one by one. After simulating the flip, it's important to restore the original state of the array. This means resetting the flipped 1 back to 0 to ensure that the array remains unchanged for subsequent iterations. Throughout this process, we maintain a variable called max_length to track the maximum length of consecutive ones found so far. For each simulated flip, we compare the current streak of ones in the modified array to this max_length, updating it whenever a longer streak is found. We also account for special edge cases. For example, if the array consists entirely of ones, the result is simply the length of the array since no flips are necessary. If the array is empty, the result is 0 because there are no elements to analyze. Similarly, if the array contains only zeros, flipping any one of them will yield a maximum streak of 1. After iterating through all indices in the array, we return max_length as our final result. The brute force approach, while straightforward, provides several key insights. First, we focus on flipping only 1 0 because the problem explicitly allows for just one flip. By iterating through all zeros in the array, we ensure that we evaluate every possible scenario where flipping might maximize the streak of ones. Although this approach is not optimal for larger arrays, its simplicity makes it a good starting point, ensuring correctness and clarity. For calculating the streak of ones in the modified array, we use a sliding window or a simple traversal, which operates in linear time for each flip. This ensures that even though we're simulating flips for each 0, the calculations for streak lengths remain computationally manageable for small to moderate input sizes. In terms of data structures, the primary structure is the input binary array itself. We might use a temporary copy during simulation, though careful in-place manipulation can avoid this overhead. Key variables include max_length for tracking the global maximum streak and current_streak for maintaining the length of the streak during traversal. Analyzing the complexity of this brute force solution, the time complexity arises from iterating through each index of the array, which is O(n), and for each 0, calculating the longest streak of ones, which is another O(n). In the worst-case scenario, if all elements in the array are zeros, this results in a time complexity of O(n²). The space complexity, on the other hand, is O(1) if we modify the array in place, or O(n) if we choose to use a temporary copy to simulate flips. While the brute force approach is simple, it is not efficient for larger arrays. To optimize, we can use a sliding window technique with 2 pointers to dynamically calculate the streak of ones while allowing at most 1 0 in the window. This reduces the time complexity to O(n), since we no longer need to simulate flips for each 0. Robust handling of edge cases, such as arrays with all ones, all zeros, or an empty array, ensures that the algorithm remains reliable under all input conditions. This Python solution solves the LeetCode problem number 487, max consecutive ones 2, using a sliding window approach to officially find the maximum length of consecutive 1s after flipping at most 1 0. We start by initializing max_ones to keep track of the longest sequence of 1s found so far. Additionally, 2 pointers left and 0_flipped are used to manage the sliding window. The left pointer represents the start of the current window, while the 0_flipped variable stores the index of the last flipped 0. The algorithm iterates through each element in nums using the right pointer. When a 0 is encountered, the left pointer is adjusted to start right after the previously flipped 0, tracked by 0_flipped, and the current 0's index is recorded in 0_flipped. This ensures that the sliding window always considers at most one flipped 0. For each step, max_ones is updated to reflect the length of the current valid window, calculated as right left plus 1. This ensures that we are always considering the longest segment of 1s with at most one flip. The algorithm runs in O(n) time, where n is the length of the input array, as each element is processed once. The space complexity is O(1), since no additional data structures are used. This makes the solution both efficient and scalable for larger input sizes. This is the Java implementation of LeetCode problem number 487, max consecutive ones 2. The logic mirrors the provided Python solution, iterating through the array while keeping track of the maximum length of consecutive ones, allowing for 1 0 to be flipped. Key differences include Java's type declarations, usage of math.max for maximum calculation, and adherence to Java's array and loop syntax. Here, we are given the input array 1 0 1 1 0 1 1 1. Initially, we set up 3 variables, max_ones to track the maximum number of consecutive ones, starting at 0, left to represent the left boundary of our window, starting at 0, and 0_flip to store the index of the 0 we can flip, initialized to -1. Now, as we iterate through the array using the right pointer, we check each element. At right equals 0, we encounter a 1, so we update max_ones to 1 by taking the maximum of its current value and the window size, which is right left plus 1. At right equals 1, we encounter a 0. Here, we adjust the left pointer to move past the previous 0 by using 0_flipped plus 1, and we update 0_flipped to the current index 1. After this, we recalculate max_ones as 2. Similarly, at right equals 2 and right equals 3, we encounter 1s, so we simply expand the window and update max_ones to 3 and then 4. At right equals 4, we encounter another 0. This means we need to move the left pointer again, this time to index 2, as the previous 0_flipped was at index 1, and we update 0_flipped to 4. The window size gives us a max_ones of 4. As we continue to process the rest of the array, encountering 1s at indices 5, 6, and 7, the window expands, and max_ones increases to 5 and finally to 6. The final result for this example is max_ones equals 6. Now, we move on to the input array 1, 1, 1, 1, 1. Again, we initialize max_ones to 0, left to 0, and 0_flipped to -1. As we iterate through the array, we notice that all elements are 1s. At right equals 0, we simply expand the window, and max_ones becomes 1. Similarly, at right equals 1, the window size increases, so max_ones becomes 2. This process continues as the right pointer moves to 2, 3, and then 4, with max_ones being updated to 3, 4, and finally 5. Since there are no zeros in this array, we don't need to adjust the left pointer or update 0_flipped. The entire array is a single window of consecutive ones, and the final result is max_ones equals 5. In this example, we have the input 0, 0, 0. As usual, we initialize max_ones to 0, left to 0, and 0_flipped to -1. At right equals 0, we encounter a 0. Since we can flip 1 0, we update 0_flipped to 0 and calculate the window size as right left plus 1, which gives us max_ones equals 1. At right equals 1, we encounter another 0. Here, we need to adjust the left pointer to move past the previous 0, so left becomes 1, and 0_flipped is updated to 1. The window size remains 1, so max_ones stays at 1. Similarly, at right equals 2, we encounter yet another 0. We adjust the left pointer again, moving it to index 2, and update 0_flip to 2. Again, the window size is 1, so max_ones remains unchanged at 1. Since all elements are zeros, the maximum number of consecutive ones we can achieve by flipping a single 0 is just 1. The final result for this example is max_ones equals 1. In this solution, we are using a sliding window approach to process the array nums in a single pass. The size of the input array is denoted as n. First, we initialize three variables, max_ones, left, and 0_flipped. These operations take constant time, or O1. Then, we enter a single loop that iterates through the array exactly once. During each iteration, we check the current element to see if it is 0, which is a constant time operation. If a 0 is encountered, we update the left pointer and the 0_flipped index, both of which are also O1 operations. After that, we use the max function to update max_ones, which, again, is done in constant time. Since there are no nested loops and every operation within the loop is O1, the overall time complexity of the algorithm is O(n). This is because we process each element of the array exactly once. Now, let's consider the best, average, and worst cases for this algorithm. In the best case scenario, if the array contains no zeros, the algorithm simply iterates through the array without needing to update the left pointer or the 0_flipped variable. Even in this case, the time complexity remains O(n). For the average case, where the array contains a random distribution of zeros and ones, the algorithm still processes every element just once, maintaining an O(n) time complexity. In the worst-case scenario, where the array alternates between zeros and ones, the algorithm processes each element individually, and the time complexity remains O(n). Moving on to space complexity, the algorithm uses only three variables, max_ones, left, and 0_flipped, each of which requires constant space, or O1. Since the input array does not contribute to extra space usage and no additional data structures are used, the overall space complexity is O1. Let's compare this solution to a naive approach. A straightforward but inefficient method would involve iterating over all possible subarrays, flipping at most 1 0 in each subarray, and counting the number of ones. Generating all subarrays would take O(n)² time, and counting ones for each subarray would take O(n). This results in a total time complexity of O(n³). In contrast, our optimized solution uses the sliding window technique to track the flipped 0 efficiently, significantly reducing the time complexity to O(n). Additionally, while the naive approach does not optimize space usage, our solution requires only constant space, or O1, for the three variables. The sliding window approach ensures that each element is processed exactly once, with no backtracking or redundant calculations. This proves that the algorithm is optimal for the problem, achieving both linear time complexity and constant space complexity. When solving this problem, there are several common mistakes to watch out for. First, not considering edge cases can lead to incorrect results. For example, arrays with all 1s or all 0s, or even empty arrays and single-element arrays, often require special attention. Always validate these scenarios to ensure your solution handles them correctly. Another mistake is implementing a brute force approach without resetting the flipped 0 back to its original state after testing. This can cause inaccurate results, so it's critical to restore the array each time. Misunderstanding the sliding window technique is another frequent issue. If you move the left pointer of the window prematurely, without verifying whether flipping the 0 is still valid, you might calculate the wrong window size. Also, ignoring constraints like the input size, which can go up to 100,000, often leads to time limit exceeded errors. You need to ensure your solution is efficient enough for large inputs. Lastly, watch out for off-by-one errors. If you forget to include the flipped 0 when computing the sequence length, your result will be too short. Paying close attention to boundary conditions and indexing can help you avoid these pitfalls. Now, let's discuss some key insights that are particularly useful in an interview setting. One important pattern to recognize is that this problem is a variation of sliding window or two-pointer problems. Many problems in interviews involve maintaining a valid window while adjusting its size based on specific constraints. Thinking about optimization is another critical aspect. While brute force is a good starting point, you should quickly transition to reducing redundant calculations, such as by using cumulative sums or sliding windows. It's also essential to explain trade-offs clearly during an interview. Compare the brute force approach with its O(n)² complexity to optimized solutions that run in O(n). Highlight how the optimizations minimize unnecessary work. Be prepared for edge cases as well, since interviewers often test solutions with arrays of all 1s, all 0s, or very small arrays of length 1 or 2. Finally, if your solution uses additional space, like in a prefix sum approach, make sure to articulate the trade-offs between time and space complexity. This demonstrates your ability to evaluate multiple dimensions of a solution. There are also several related problems that share similar concepts. For example, LeetCode 424, longest repeating character replacement, is another sliding window problem where you replace characters to form the longest valid substring. LeetCode 1004, max consecutive ones 3, is a direct variation of our problem where you can flip up to k zeros instead of just 1. LeetCode 485, max consecutive ones, is a simpler version where no zeros are flipped, making it a great starting point for beginners. Lastly, LeetCode 3, longest substring without repeating characters, is another classic sliding window problem that focuses on substrings rather than arrays. Exploring these problems can help you deepen your understanding of the sliding window technique and recognize its applications in various scenarios. To wrap up, let's look at some alternative approaches to solving this problem. The optimized sliding window technique uses 2 pointers to maintain a valid window with at most one flipped 0. You expand the right pointer to include more elements and move the left pointer when the count of flipped 0s exceeds 1. This method is efficient, running in O(n) time, but requires careful handling of the window boundaries to ensure correctness. Another approach is using a prefix sum. By calculating the number of 1s in any range, you can determine the maximum sequence length after flipping 1 0. While this method has higher space complexity at O(n), it can be easier to implement in some cases. Lastly, there's the brute force approach, where you flip each 0 to 1 and calculate the longest sequence of 1s for each modified array. Though simple to implement, this method runs in O(n)² time, making it inefficient for large arrays. Each approach has its trade-offs, so choose based on the problem constraints and your goals. Great job! We've wrapped up the problem max consecutive ones too. We reviewed approaches, complexities, and key problem-solving strategies. Remember to practice similar problems to master these techniques. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!